In this lecture, we are going to discuss the basic concept of magnetism. Similarly to the electrical charges, which are positive and negative charges, the magnets have north pole and south pole. Opposite magnetic poles attract and like poles repel. The magnetic properties seems to be concentrated in the poles. We can see in this picture more iron filings are attracted to the poles. But one difference between electrical charges and magnetic poles is the magnetic poles always come in pairs. If we cut a magnet bar in halves, we will have a new complete magnet with both north pole and south pole. Each of these poles is called monopole. The separation of a pair of poles into monopoles has never been accomplished. Similarly to the electric field, the magnets change the space around them. If we move a magnet in a space near to a second magnet, it experiences a magnetic field. The magnetic field can be represented by field lines. In this picture, we can see the field lines that is forming by the iron filings. Also, we can see in this picture the strength of the magnetic field is greater where the lines are closer and weaker where the lines are farther apart. One more thing is the lines of the magnetic field always start in the North Pole and end in the South Pole. These lines are a map of the magnetic field around a bar magnet. Now let's talk about the Earth's magnetic field. The Earth's magnetic field is originated by the electric currents due to the motion of molten metals in its core. That metals can be iron or nickel. Also, we know the needle of the compass is itself a magnet. This is why the north pole of the compass is the magnetic north pole. But what happens is the north pole of the compass is attracted by the north geographical pole of the Earth. If these two attract, means this corresponds to the south magnetic pole. Then this is why also the south geographical pole of the Earth corresponds to the magnetic north pole. Now let's see the relation between electric currents and magnetism. During 1800s, Hans Christian Oersted, he observed when the current flowed through the wire, the magnetic compass was deviating. Since the needle of the compass is a magnet itself, he concluded that the electric current that flowing in the wire produces a magnetic field. Then he demonstrated that an electric current produces a magnetic field. The Christian Oersted observation was the base of electromagnetic effect. And let's see what is the electromagnetic effect. And we already say when the current flows to the wire is create a magnetic field. As this is we represent in this picture. Now, if the wire is formed into loops, the line of the electric field concentrate, which increase the magnetic field. And we can see in this picture, we have more lines of magnetic field. And then they will create a magnet with north and south poles. Now let's see what happened if we now had many loops. Yes, that is forming into cylindrical coil like we had in this picture. And this, when we had many loops formed into cylindrical coil, this is called a solenoid. When the current flows through the solenoid, a magnetic field is created, and that magnetic field acts like a magnet. And this effect is called electromagnet. And let's review what is electromagnetic effect. And when the current is flowing through the solenoid, it produces a magnetic field like the magnetic field we had in the any bar magnet or a permanent magnet. This effect is important for many applications and is used in many devices that we use every day. For example, is used in electromagnetic switches like magnetic locks, speakers, microphones, memory stick, magnetic resonance imaging, and fast trains. Another application of the electromagnetic effect is the motor. An electrical motor is a device that converts electrical energy into the mechanical energy, means into the motion energy. A motor has two working parts, a stationary or permanent magnet and movable electromagnet, which is called armature. If the armature is connected to a source of power, then the current starts flowing and creates a magnetic field. This is why the armature will have north and south pole also. The north and south pole of the armature will be attracted and repelled with the poles in the permanent magnet, and this creates a motion in the armature. Then this armature will be spin 180 degrees. The motion of the armature is used to do work. But this is just a simple diagram of a motor. The real motors are a little more complex, and they will have more than one loop, and the reason is because if they had more than one loop, many loops, then it will increase the spin of the rotation, and also in this way they will get uniform movement. Some of the applications of the electric motors are, for example, the fan, the blender, or washing machines are also another example of the electric motors. And remember, electric motors convert electrical energy into mechanical energy, into motion energy. We already studied that electricity can induce magnetic properties, and now we are going to see that magnetic can induce electricity. When the magnet is moved through a loop of wire, or vice versa, when the magnet is moved through the loops, it induces a voltage, which results in an induced current. The magnitude of the voltage depends on the number of wires, loops, that depends on how many loops we had, the strength of the magnetic field, the rate at which magnetic fields are cut by the wire is how fast we move the magnet. Also, the direction of the current depends on the direction of the motion. As this is, we can see here, the direction of the current depends on the direction of the motion. And this interaction is called electromagnetic induction and is explained in the Faraday's law of induction. One of the applications of the electromagnetic induction is the generators. A generator is a device that converts mechanical energy into electrical energy. In this case, we had a magnet, permanent magnet, and we had a rotating loop. When the loop moved inside the magnet, induce a voltage which create an electrical current that generate electricity. And let's watch in the next video in this video they explain in detail what is a generator.
How do power stations provide electricity to thousands of houses around a city? They don't use giant batteries. They do that by spinning a giant turbine like this. And to spin such a turbine, some power stations use very hot steam that blows over the turbines and spins it. Or maybe we can use the energy of the falling water. Or another example could be we fit these inside giant windmills and let the wind do the work for us. Whichever way you choose, all we do is spin a giant turbine. But how does turning something create electricity? Well, the technology is based on electromagnetic induction, discovered by Michael Faraday more than 200 years ago. The basic idea is that if you take a wire and move it up or down inside a magnetic field, it induces an electric current. So all we have to do is attach a coil of wire to these giant turbines and place them inside a magnetic field. As the turbine rotates, the coil starts rotating and the wires start moving up and down inside the magnetic field. That produces the electric current. And this can now be used to light up things. These devices are called electric generators. They convert spinning or mechanical energy into electrical energy.
Just to review, one of the applications of the electromagnetic effect are the motors, and motors convert electrical energy into the mechanical energy. One of the applications of the electromagnetic induction are the generators, and generators convert mechanical energy into electrical energy. This is all I had to discuss for today.